If there were one word to epitomize SpaceX, adaptability would undeniably be the ideal selection. In the aftermath of Starship Flight 3, SpaceX promptly marshaled its resources to tackle the encountered challenges and gear up for the subsequent launch. With a projected time frame of 6 weeks, SpaceX aims to attain readiness for Flight 4. New modifications are in the pipeline for Ship 29 and Booster 11, tailored to address the issues identified during the launch process and ensure smoother operations in the upcoming mission. So today, let's take a look at the newest design that SpaceX will use for Ship 29 and Booster 11 in the near future. First up, the recent adjustment to the grid fins of the booster stems from observations during the landing process of Booster 10, which underscored a critical area requiring enhancement in SpaceX's Starship program. Notably, during the landing sequence, Booster 10 exhibited significant instability, with its grid fins rolling and shaking vigorously in an uncontrollable manner. While SpaceX has not officially addressed this issue, there are intriguing speculations regarding its root causes. One potential factor contributing to the instability of the grid fins could be related to the control capabilities within the drive system. These fins are controlled by actuators responsible for managing pitch, yaw, and roll adjustments. The choice of power sources for these actuators is paramount, and SpaceX has implemented an electronic steering system without hydraulic fluid for this purpose. However, past instances have revealed instability in this system, such as the delay in Starship Flight 2 due to actuator replacement on a fin. Another plausible explanation for the erratic behavior of the grid fins could be electrical supply interruptions. These fins are electrically activated and powered by the ship's electrical system, with SpaceX employing Tesla batteries to operate this system. Nevertheless, as seen in previous incidents, issues may still arise with this battery type. Grid fins serve as a unique type of control surface, akin to an aircraft's flaps or rudder, providing aerodynamic pitch, yaw, and roll control during descent through the Earth's atmosphere. Unlike those of Falcon 9, the Super Heavy booster and Falcon 9's first-stage booster grid fins are fixed and do not fold during ascent, as the addition of a folding mechanism would increase weight and complexity. The 4 grid fins on Super Heavy each weigh 3 metric tons, considerably heavier than those of Falcon 9. Despite their relatively flat appearance, these fins possess a substantial surface area due to their composition of numerous smaller fins, aiding in aerodynamic control and stability during descent. The simulations conducted by SpaceX suggest that the grid fins are not expected to significantly impact the efficiency of Super Heavy during ascent. This is primarily attributed to the larger size of Super Heavy compared to Falcon 9, resulting in aerodynamic drag playing a relatively minor role due to the square-cubed law. Instead, the rocket's mass and gravitational forces have a more pronounced effect on performance during ascent. Nevertheless, the performance of this component remains a focal point for SpaceX in upcoming Starship flights. Adjustments may be necessary based on the challenges encountered in Starship's Flight 3, or they could involve optimization efforts, as Elon Musk has previously indicated. Musk has acknowledged that the grid fins are somewhat over-engineered or not fully optimized, drawing from SpaceX's experience with Falcon 9. The decision to utilize grid fins in the initial iterations of Starship was driven by a desire to expedite development, with plans to refine or replace them as more data is gathered. Musk has hinted at potential improvements in the design of Booster 11, raising anticipation for the enhancements to come. This could involve making the grid fins lighter and potentially smaller, with the possibility of reducing their number from 4 to 3 and introducing smarter technology for improved functionality. The booster landing process was also marred by concerns surrounding the performance of the Raptor engines. Evidence suggests that the booster may have descended too rapidly, with the engines failing to ignite properly as it approached the ground, resulting in a fiery landing just 1 kilometer above the surface. Analysis indicates that although 3 engines attempted to ignite, the booster did not exhibit significant deceleration, leading to the missed target landing time of T+6.52 minutes. Of particular note during the descent is the observation of an object ascending from below and striking one of the grid fins, causing paint to peel off. This object was identified as a fragment of the engine base shielding, dislodged during the malfunctioning or damage of the Raptor engine, likely due to the intense forces experienced during the high-speed return at speeds exceeding 4,000 km/h. This compromised engine performance resulted in insufficient thrust to execute the landing process accurately. Consequently, the Raptor engines present a formidable challenge for SpaceX, prompting a re-evaluation of their technical procedures for installing the 33 engines on the booster. Addressing these issues will be crucial for ensuring the reliability and success of future missions. SpaceX did not raise significant issues with Starship Stage 2 during the launch. Observations from the space community indicate that Ship 29 requires further reinforcement, particularly in its heat shield. The heat shield plays a crucial role in safeguarding the spacecraft from the extreme heat generated during re-entry into Earth's atmosphere. Concerns have been raised regarding the retention of heat shield tiles during re-entry, with instances of tiles falling off observed in previous missions. The primary issue lies in the process of attaching the Thermal Protection System (TPS) tiles. Premature detachment of these protective components has been noted, potentially stemming from loosely tightened bolts or damaged clip heads. Despite the vibrations and pressures experienced during the launch, relatively intact TPS blocks have been discovered near the launch site, indicating possible issues with the installation process. The complexity of verifying the correct installation of each of the 18,000 tiles poses a challenge, and factors such as stacking, destacking, tanking, detanking, and thermal expansion may contribute to tiles coming loose before launch. With multiple attachment points, the failure of one pin can lead to the entire tile becoming compromised. While the performance of the tiles during re-entry remains uncertain, SpaceX's thermal management efforts are expected to mitigate heat-related challenges. However, even the most robust tiles will be ineffective if they detach during flight. SpaceX will need to conduct tests to assess the tile's ability to withstand the stress of re-entry. Until better solutions are identified, the current tiles should suffice for Starship missions, albeit with continued monitoring and evaluation. In addition to the modifications made to Ship 29, attention has been drawn to the functionality of its payload bay, which appears to have fallen short of expectations, as indicated by SpaceX's tweet. The payload bay door has encountered issues with opening and closing properly, with reports of it unexpectedly popping open during the spacecraft's flight in space. To address these concerns, the redesigned Starship is anticipated to incorporate an altitude control system known as the Reaction Control System, RCS. This system, which helps maintain stability during gliding with its wings, has already been partially implemented in the initial phase of Starship. However, the full functionality of the RCS may not yet be operational, as it requires the addition of position control units. As is often the case, the completion of these modifications may take longer than initially anticipated. Currently, only the new booster features the updated design, with plans for the spacecraft to undergo refurbishment in a subsequent update. As SpaceX meticulously analyzes and learns from each previous flight, addressing the challenges encountered will be paramount in refining and optimizing the Starship program. By identifying and rectifying inherent weaknesses in components and attachment processes, SpaceX aims to bolster the reliability and performance of the spacecraft for future missions. Anticipation builds for the next flight of Starship, where we can expect to witness a new and improved iteration, poised to shine brightly as it continues to push the boundaries of space exploration. Thank you for tuning in. Remember to like and subscribe for more videos on the future of Elon Musk and SpaceX's ambitious Starship program.